In this example, we're asked to calculate the directional derivative for the surface f at xy is equal to xy at the point 2, 3, and we're going to slice that surface with a plane in the direction of this vector v. In order to calculate the directional derivative, we basically need three things. The first is that we need a unit vector in the direction of the slicing plane. We have a vector in the direction of the slicing plane, but it's not a unit vector. We need the magnitude of that vector to be 1, so we'll have to work on this a little bit. Then we're going to need the first partial of f with respect to x evaluated at our domain element, and our domain element is 2, 3, so that's what we'll plug in to that first partial, and then also the first partial with respect to y, also evaluated at 2, 3. Let's recall that in order to find a unit vector in the direction of v, the formula is that our unit vector will be v divided by its own magnitude. So mag v is going to be the square root of 1 plus 1, because our v vector is basically 1, 1, and we're squaring those components and adding them together to get 2. So u is going to be the v vector divided by its own magnitude, or just 1 over square root of 2 times the v vector, which also works. I'm going to then distribute this scalar quantity into that vector to get 1 over rad 2, 1 over rad 2. And I'm not going to bother rationalizing the denominator. So we'll come back to this in a bit. Next, we need to calculate the first partial with respect to x. So the original surface function was x times y. So the first partial with respect to x is just going to be y, and the first partial with respect to y is just going to be x. So if I evaluate the first partial with respect to x at the 2, 3 ordered pair, the y value is 3, so the output here is 3. Evaluating the first partial with respect to y at 2, 3, the x coordinate is 2, so the output is 2. And so now we'll take all three of these pieces and plug them back into the formula for calculating that directional derivative. So the directional derivative evaluated at the ordered pair 2, 3 is going to be the first partial with respect to x evaluated at 2, 3, which we found to be 3, times a, which is the horizontal component of our unit vector, and so in this case our unit vector AB quantities are both 1 over square root of 2, plus to that we're going to add the first partial with respect to y evaluated at 2, 3, which we found to be 2, and then we'll multiply that by the b component of our unit vector, which again is 1 over rad 2. So when we add all this together, we get 5 over radical 2, and this is the value of that directional derivative, so our final answer. Now remember, this is a scalar quantity because it represents the slope of a tangent line.